Hello, this is Geometry. We'll be starting Chapter 9, which deals with right triangles. And then in 9.1, we'll specifically be talking about the Pythagorean theorem. Before we start talking about the Pythagorean theorem, let's review a right triangle. So in a right triangle, triangle ABC, and I'm going to let C be the right angle. Really, when you're setting up a right triangle, you should always let C be the right angle. I'll show you why in a minute. But first of all, each of the sides that make up the right angle, in this case, side length AC and side length CB, are the legs of the right triangle. And then the side opposite the right angle, or the side that doesn't make up the right angle, is the hypotenuse. For simplicity's sake as well, side length CB is opposite angle A. So instead of referring to that as side CB, I'm going to use a lowercase letter to represent the sides. So since it's opposite angle A, I'm going to let that be A. AC is opposite angle B, so that's lowercase b. And then AB is opposite angle C, that's side length C. And then the Pythagorean theorem, you probably already know it, and you probably remember it as A squared plus B squared is equal to C squared. That's fine if you remember it like that. But really what the Pythagorean theorem states is the sum of the squares of the legs of a right triangle is equal to the hypotenuse squared. So there's the Pythagorean theorem written out in words. Just be careful. You can only use the Pythagorean theorem for right triangles. Don't try to use the Pythagorean theorem for non-right triangles. And then it would be helpful for you to know certain what are called Pythagorean triples. Pythagorean triples are just three whole numbers that make up or satisfy the Pythagorean theorem. For example, probably the most common or the most well-known Pythagorean triple are 3, 4, and 5. The reason why 3, 4, and 5 make up a Pythagorean triple is 3 squared, 9, plus 4 squared, 16, is equal to 5 squared, which is 25. Those are three whole numbers that satisfy the Pythagorean theorem. So 3, 4, 5 is a Pythagorean triple. And then any multiple of 3, 4, and 5. For example, if I multiply each of these by 2, 6, 8, and 10 make up a Pythagorean triple as well. 6 squared plus 8 squared equals 10 squared. If you don't believe me, try it. I can multiply each of these by 3 as well. 9, 12, and 15 make up a Pythagorean triple as well. And so on. But besides 3, 4, and 5, don't think just because 3, 4, and 5 make up a Pythagorean triple that any three consecutive numbers make up a Pythagorean triple. You can even try it. Try 4 squared plus 5 squared and see if that's equal to 6 squared. It doesn't. Okay, so not any three consecutive numbers make up a Pythagorean triple. But the next Pythagorean triple is 5, 12, and 13. 5 squared, 25, plus 12 squared, 144, is equal to 13 squared, 169. And then I can do a similar thing with 5, 12, and 13. 10, 24, and 26 should work because that's 5, 12, and 13 multiplied by 2. And then I can multiply 5, 12, and 13 by 3 as well. But another Pythagorean triple is 8, 15, and 17. 8 squared, 64 plus 15 squared, 225 is equal to 17 squared, 289. And then again, any multiple. So 16, 30, and 34 would work. And just one other, even though there's more Pythagorean triples, but another Pythagorean triple, 7, 24, and 25. Those make up a Pythagorean triple. And like all the other ones, any multiple, any whole numbered multiple. So 14, 28, and 50 would make up a Pythagorean triple.